Hello everyone, and thanks for attending my talk. My paper title is Proper Orthogonal Decomposition Reduced Order Model for Tear Film Flows. I'm Samir Sahyun from Uppsala University. My colleagues in this paper are Dan Wilson, Sadiq Jawadi, and Steve Weiss from the University of Tennessee, USA, and Hamid Abdurrahmani from Khalifa University, UAE. So first, let me introduce the problem. So the tear film is a multi-layer structure. Um, its purpose is to protect the eye, the general purpose. Now, some problems might happen in some cases where the tear film shrinks between blinks after the eye opens. The tear film thickness can go to 0. This sometimes causes problems, dry spots over the cornea, irritation, discomfort, headaches. So many problems can happen. We want as much as we can to avoid the tear film thickness from going to 0. A famous disease, dry eye syndrome, um, is a result from frequent um, 0 thickness situations. So models for the tear film dynamics are developed in the literature. Um, we used in this paper the IDMIR model because it couples the tear film thickness dynamics with the lipid concentration dynamics, because we thought that in the future we might use the lipid concentration as a control variable to achieve our control goal. And I will talk about that later in the talk. So the objective is to construct a reduced order model out of the PDE infinite dimensional system here, so that we have a model that we can easily use well-developed techniques in the literature to do the control design. The ultimate goal, we think that we might come up with smart tiers that with a surfactant that can modify the surface tension to prevent the tear film from the thickness for the tear film from to, to go to 0 or to break up. We use proper orthogonal decomposition and Galerkin projection. So this is the how the model looks like. We have the dynamics of the thickness coupled with the dynamics of the lipid concentration. H is the thickness, gamma is the lipid concentration. Now, we assume that the lower eyelid is stationary, and when you open your eye, the upper eyelid moves with the position L of t and speed Lt of t. The problem with this situation is that we have a moving boundary a problem, which is a challenging problem numerically. So we need to transform this moving boundary to a fixed boundary. Basically, we will move this mobility to the PDE domain. Parameters here: M is the Marangoni number, C is the capillary number, B is the bond number. These are the initial conditions and boundary conditions. As I said, at x equals 0, this is the lower eyelid, but at x equals L of t, we have a problem here. So a well-known technique to tackle this problem is to use a change of variable for X and H. So before I go there, these are the profiles of the position of the upper eyelid and the speed. So at L equals 1, it is the fully open eye. And this is the speed of the opening, the orange one. Now, using this change of variables, we add these terms as a result. So full details are explained in the paper of how we do the transformation. But now we don't have a moving boundary, we have a fixed boundary. We still have a time-dependent values in the boundary conditions. Remember that L is a time-dependent variable, and LT, of course. The problem, this is a numerically challenging problem because we have a fourth order of nonlinearity here, and a fourth order of also a special derivative here. 3, and this is the fourth one. We used finite difference method with cell edge and cell center points technique. Our colleague Steve Weiss from the University of Tennessee helped us with this. We used these values of the parameters, and these are the results of the simulation. This is the early stage thickness dynamics. This is the mid stage. This is the late stage. I want you to notice that at late stage, the thickness is so close to 0, and this is the problems that I was talking about. We want to prevent this. We want to keep it like this, or maybe even better, but we don't want something that goes to 0. And this is the lipid concentration, which also goes to some low values, but this is not the main parameter. We want to use this possibly as a control variable to prevent unwanted situations here. Pod, I don't want to spend, I don't have much time left, so I don't want to spend so much time in pod. So we construct the pod modes using the eigenvalue problem, which is the well-known solution for the pod minimization problem. And we find the pod modes. And then we find the discrete temporal coefficients because we want to use them to compare our reduced order model to make sure it's valid. These are the pod modes for H and the pod modes for gamma. And now the Galerkin projection, we project the PDE system onto the pod modes to get this finite dimensional system. We used 4 modes, so this is order of 4. Again, full details are in Appendix B if you want the full details of the structure F of alpha. These are the results. The orange curves are the states. These are the solution for this system. And the blue ones are the discrete ones that I talked about, the reference. We want them to agree. As shown, they agree at the later stages. But in the early stages, not so much agreement, but it's good enough that they eventually agree. This is a comparison between the full order and reduced order models at early stage and at late stage. As you see, at early stage, it's not a good agreement, but eventually the solution agrees. This is gamma as well, the same thing. And I will skip the conclusions. If you have questions, just ask me in the questions section. Thank you very much.